So here's something to think about as you lie there tonight. Right now, in this exact moment, you are made of particles, not in some poetic, hand-wavy sense. Literally. Every single thing about you, the weight of your body pressing into the mattress, the warmth of your skin, the thoughts drifting through your mind, all of it comes down to a handful of tiny, fundamental particles interacting with each other according to a small set of rules. And when I say handful, I really do mean that. The entire visible universe, everything you have ever seen or touched or tasted, every star, every planet, every grain of sand on every beach, every drop of water in every ocean, all of it is built from just 17 types of particles. 17! That's fewer than the number of keys on a piano octave. The universe has an almost absurdly short ingredients list, and yet from those few ingredients, it somehow produces everything. Galaxies, thunderstorms, oak trees, you. And there's a theory that describes those particles and how they interact. A theory that physicists spent the better part of the 20th century slowly, painstakingly piecing together. It's called the Standard Model of Particle Physics, and it is, by certain measures, the most successful scientific theory in human history. Its predictions have been confirmed to extraordinary precision, sometimes matching experiments to 10 or 12 decimal places. It tells us what matter is made of at the most fundamental level we've ever been able to probe, and it describes 3 of the 4 known forces of nature in a single, unified mathematical framework. It is, in a very real sense, the instruction manual for reality. And yet, almost nobody outside of physics has any idea what it actually says. If you stopped 100 people on the street and asked them what the Standard Model is, you might get 1 or 2 who could give you a vague answer involving quarks or the Higgs boson. The rest would look at you blankly. And that's a shame, because the story of how we figured all this out, the discoveries, the arguments, the wild guesses that turned out to be right, the beautiful experiments, the personalities involved, it's one of the great intellectual adventures of the 20th century. And it's what we're going to talk about tonight. So get comfortable, let your eyes close if they want to. We're going to start at the very beginning and work our way through the whole thing, step by step, slowly, in no particular hurry. If you drift off along the way, that's perfectly fine. That's kind of the point. The particles will still be there in the morning. They've been there for about 14 billion years. They're not going anywhere. Let's start with the oldest version of this question, which is, what is stuff made of? What's the smallest piece of something you can get? If you take a chunk of gold and cut it in half, then cut the half in half, then cut that in half, and you keep going, keep cutting, what happens? Can you keep going forever, getting smaller and smaller pieces of gold without limit? Or do you eventually reach something that can't be cut any further, some fundamental unit, some smallest possible piece? This question is at least 2,500 years old. The ancient Greeks wrestled with it, and they came up with both possible answers. On one side, there were people like Aristotle, who argued that matter is continuous. You can divide it infinitely, and there's no bottom level. On the other side, there were the atomists, most famously a philosopher named Democritus, born around 460 BCE, in the Greek city of Abdera, in what's now northern Greece. Democritus argued that if you keep cutting, you eventually reach something indivisible, something that cannot be broken down any further. He called these things atomos, which literally means uncuttable in Greek. Atoms. Now, Democritus didn't have any experimental evidence for this. He couldn't look at atoms. He couldn't weigh them or bounce things off them. It was pure reasoning, pure philosophy. He was essentially asking a logical question about the nature of matter, and he arrived at an answer that turned out to be remarkably close to right, although the details would take another 23 centuries to work out. And for most of those 23 centuries, the atomic idea was just that, an idea, a philosophical position, not a scientific one. It sat there, dormant but not forgotten, occasionally picked up and discussed by various thinkers across the centuries, but never really testable. That started to change in the late 18th and early 19th centuries, when chemistry began to mature as a science, and the person who turned the atomic idea from philosophy into something that looked a lot more like physics was an English schoolteacher named John Dalton. Born in 1766 in a small village in the Lake District, Dalton was modest, methodical, and colorblind. He actually did important early research on colorblindness, which is still sometimes called Daltonism in some languages. But his real contribution was to chemistry. In the early 1800s, Dalton noticed something striking about the way elements combine to form compounds. They always combine in simple, whole number ratios. Water is always 2 parts hydrogen to 1 part oxygen. Carbon dioxide is always 1 part carbon to 2 parts oxygen. Not 1.5 parts, not 2.7. Always simple, clean integers. And Dalton realized that this makes perfect sense if matter is made of discrete, indivisible particles, atoms, and if each element has its own kind of atom with its own specific weight. If a water molecule is made by combining exactly 2 hydrogen atoms with exactly 1 oxygen atom, then of course the ratio is always 2 to 1. You can't have half an atom. The whole number ratios are a natural consequence of the atomic hypothesis. It was elegant, it was simple, and it explained a growing body of chemical data beautifully. By the mid-19th century, the atomic theory of matter was widely accepted among chemists, even if nobody had actually seen an atom or had any idea what one looked like on the inside. And for a while, the picture was fairly tidy. Each element corresponds to one type of atom. Atoms are indivisible, and all the chemistry we observe comes from atoms combining and recombining in different ways. Neat, clean, simple. But then, in the closing years of the 19th century, that tidy picture started to unravel, because it turned out that atoms are not indivisible after all. They have parts, they have an inside, and figuring out what that inside looks like would be the first step on the road to particle physics, and eventually, the Standard Model. The first crack appeared in 1897, in a laboratory at the Cavendish Laboratory in Cambridge, England. A physicist named J.J. Thomson was experimenting with cathode rays. These are the beams you get when you apply a high voltage across a sealed glass tube, with most of the air pumped out. They were mysterious. Nobody was sure what they were. Some physicists, particularly the Germans, thought they were a kind of wave, like light. Others, particularly the British, suspected they were streams of particles. Thomson designed a series of brilliant experiments to settle the question. He showed that cathode rays could be deflected by both electric and magnetic fields, which meant they carried electric charge, and by carefully measuring how much they were deflected, he could calculate the ratio of their charge to their mass. And here's what was shocking. Whatever these particles were, they were incredibly light. Roughly 2,000 times lighter than a hydrogen atom, which was the lightest atom known. And they were the same, regardless of what material the cathode was made of. Whether you used aluminum or iron or platinum, you got the same particles with the same charge-to-mass ratio. Thomson had discovered the electron, the first subatomic particle, the first piece of evidence that atoms are not the end of the story, that there's a deeper level, and he'd found it in every kind of atom he tested, which meant that electrons are a universal ingredient. Every atom contains electrons. Democritus's uncuttable atom had been cut. Now, finding electrons inside atoms immediately raised a question. What's the rest of the atom like? Electrons are negatively charged, but atoms as a whole are electrically neutral. They have no net charge. So there must be something positively charged in there too, something that balances out the electron's negative charge. But what? And how is it all arranged? Thomson proposed a model, the plum pudding model, which we talked about a few moments ago, in a different context. He imagined the positive charge spread out like a smooth, diffuse blob, with the electrons embedded in it like raisins in a pudding. It was a reasonable first guess. And it was completely wrong. We know it was wrong because of Ernest Rutherford. New Zealand-born, big personality, booming voice, a man who once said that all science is either physics or stamp collecting, which tells you something about his ego, but also about his passion for getting to the bottom of things. Rutherford had won the Nobel Prize in Chemistry in 1908, which he found somewhat ironic since he considered himself a physicist, and in 1909, working at the University of Manchester, he set two of his researchers, Hans Geiger and Ernest Marsden, to work on an experiment that would blow the plum pudding model to pieces. The experiment was conceptually simple. You fire alpha particles. These are small, heavy, positively charged particles emitted by certain radioactive elements, essentially helium nuclei, at a very thin sheet of gold foil, and you see what happens. If Thomson's model were right, if the positive charge inside an atom were spread out smoothly, like a cloud, then the alpha particles should mostly pass straight through with only tiny deflections, like bullets through fog. And indeed, most of them did exactly that. But some of them didn't. Some deflected at large angles. And a tiny fraction, roughly 1 in 8,000, bounced almost straight back toward the source. Rutherford later said, this was the most astonishing result he'd ever encountered in his life. He compared it to firing a 15-inch artillery shell at a piece of tissue paper and having it come back and hit you. What those results meant, when Rutherford worked through the mathematics over the following months, was that almost all of the atom's mass and all of its positive charge had to be concentrated in an incredibly tiny, incredibly dense region at the center. He called it the nucleus, and the numbers were staggering. The nucleus was roughly 10,000 times smaller than the atom itself. If you scaled an atom up to the size of a cathedral, the nucleus would be a fly buzzing around somewhere near the altar. The rest was empty space, with electrons orbiting somewhere out in the vast emptiness. This was 1911, and it gave us the basic architecture of the atom that we still use as a starting point today. A tiny, dense, positively charged nucleus at the center, with negatively charged electrons somehow existing around it in the vast surrounding space. But Rutherford's model immediately raised new questions. What's the nucleus itself made of? What's inside it? And what holds it together? Because think about it. If the nucleus is positively charged, and it contains multiple positive charges, all crammed into a fantastically tiny space, those positive charges should be repelling each other with enormous force. The electromagnetic repulsion between them should be tearing the nucleus apart. What's keeping it from flying to pieces? The answer to the first question, what's the nucleus made of, came in stages. Rutherford himself had identified the proton by 1920, showing that the hydrogen nucleus is a fundamental positively charged particle present in all nuclei. The name proton comes from the Greek word for first. Each element is defined by the number of protons in its nucleus. Hydrogen has 1, Helium has 2, lithium has 3, carbon has 6, gold has 79. The number of protons is what makes an element what it is. Change the number of protons, and you change the element entirely. But there was a puzzle. If you looked at the masses of different nuclei, they were heavier than you'd expect from just counting protons. Helium, with 2 protons, has a mass of about 4 atomic mass units, not 2. Carbon, with 6 protons, has a mass of about 12, not 6. Something else was in there, adding mass without adding electric charge. For years, some physicists speculated that nuclei might contain extra protons, paired with electrons that canceled their charge. But that idea had problems, and it never quite worked out. The answer came in 1932, from James Chadwick, a British physicist working at Cambridge who had been a student of Rutherford's. Chadwick had been looking at some puzzling experiments involving beryllium. When you bombarded beryllium with alpha particles, it emitted a mysterious, penetrating radiation that didn't seem to be gamma rays and didn't behave like any known particle. Chadwick showed that this radiation consisted of particles with roughly the same mass as a proton, but no electric charge. He called them neutrons. And suddenly, the picture of the nucleus snapped into focus. Every atomic nucleus is made of protons and neutrons packed tightly together. The protons carry the positive charge. The neutrons carry no charge but contribute mass. Hydrogen has 1 proton and no neutrons. Helium has 2 protons and 2 neutrons. Carbon has 6 protons and 6 neutrons, and so on, all the way up the periodic table, with nuclei getting bigger and heavier as you add more protons and neutrons. The neutron was the last big missing piece of the atomic puzzle, and Chadwick won the Nobel Prize for it in 1935. So by the early 1930s, the picture looked like this. The universe is made of atoms. Atoms are made of electrons orbiting a nucleus. The nucleus is made of protons and neutrons. 3 particles, electron, proton, neutron, and that's everything. All of chemistry, all of biology, all of geology, all of everything you can see and touch, built from just 3 types of particle. It was beautiful in its simplicity, and it was about to get enormously more complicated. Because here's the thing about physics. Just when you think you've found the bottom, just when the picture looks clean and complete, something comes along and shows you that there's another layer, that the things you thought were fundamental are actually made of smaller things, or that there are entirely new particles you never expected, lurking in places you hadn't thought to look. And that's exactly what happened in the 1930s, 1940s, and 1950s. The story of particle physics is, in a very real sense, the story of simplicity giving way to bewildering complexity, and then, slowly, painfully, a new, deeper simplicity emerging from the chaos. But we'll get to that. First, we need to talk about antimatter, because the discovery of antimatter is one of those moments in physics where pure mathematics predicted something so outrageous, so seemingly impossible, that even the person who did the math wasn't sure what to make of it. The person at the center of this story is Paul Dirac, and Dirac is one of those figures in the history of physics who deserves to be as famous as Einstein, but somehow isn't. Born in Bristol, England, in 1902, Dirac was almost pathologically quiet. He spoke only when he had something precise to say, and even then, he used as few words as possible. There are legendary stories about Dirac's economy with language. When Niels Bohr once complained that he didn't know how to finish a sentence in a paper he was writing, Dirac allegedly replied, "I was taught at school that you should never start a sentence without knowing the end of it." At a lecture, someone once said, "Professor Dirac, I didn't understand the equation on the top right of the blackboard, and Dirac just stood there, silently. After an awkward pause, the moderator said, "Professor Dirac, aren't you going to answer the question?" And Dirac said, "That wasn't a question, it was a statement. That's Dirac." But behind that silence was one of the most powerful mathematical minds in the history of science. And in 1928, at the age of 25, Dirac did something extraordinary. He wrote down an equation, the Dirac equation, that combined quantum mechanics with Einstein's special theory of relativity to describe the behavior of the electron. This was a problem that had been nagging physicists for years. The existing quantum mechanical equations, like Schrödinger's equation, worked beautifully for slow-moving particles, but they weren't compatible with special relativity. They didn't account for the fact that energy and mass are related, that particles moving close to the speed of light behave differently. Dirac set out to fix that, and the equation he came up with was elegant, compact, and almost immediately recognized as a work of genius. But the equation had a surprise in it. When Dirac solved it, he found that it had two sets of solutions. One set described the electron perfectly, its energy, its spin, its magnetic properties, all matching experimental data beautifully. But the other set of solutions described something else, something with exactly the same mass as the electron, exactly the same spin, but with a positive electric charge instead of a negative one. A mirror image of the electron, identical in every way, except that its charge was flipped. Dirac wasn't sure what to make of this. He tried various ways to explain away these extra solutions, to dismiss them as mathematical artifacts, but they wouldn't go away. The equation demanded them. And eventually, Dirac made a prediction that sounded like science fiction. There must exist a particle that is the mirror image of the electron, a positively charged electron, an anti-electron. The first hint that for every particle in nature, there might be a corresponding antiparticle. This was 1930, and most physicists were skeptical. An anti-electron? It sounded absurd. But then, in 1932, the same year Chadwick discovered the neutron, an absolutely banner year for particle physics. A young American physicist named Carl Anderson was studying cosmic rays at the California Institute of Technology. Cosmic rays are high-energy particles that rain down on Earth from outer space, smashing into the atmosphere and producing showers of secondary particles. They were, for decades before particle accelerators became powerful enough, the main way physicists discovered new particles, nature's own atom smasher, running constantly, for free. Anderson had a cloud chamber, which is a beautiful device. It's essentially a sealed container filled with supersaturated vapor, alcohol or water vapor, and when a charged particle passes through it, it leaves a trail of tiny droplets, like a jet leaving a contrail across the sky. If you put the cloud chamber in a magnetic field, the trails curve, and the direction and tightness of the curve tell you the particle's charge and momentum. Anderson was photographing these trails, studying the particles produced when cosmic rays hit the atmosphere, and one day he saw something he couldn't explain. A trail that curved the wrong way. It looked exactly like an electron, same mass, same amount of curvature, but the curve bent in the direction that meant positive charge instead of negative. He had found the positron, the anti-electron. Dirac's seemingly crazy prediction, confirmed in a cloud chamber photograph. It was one of those moments where theoretical physics and experimental physics lock together with an almost audible click. Anderson won the Nobel Prize for this discovery in 1936. Dirac had already won his in 1933, in part for the equation that predicted it. And the discovery of the positron opened up an entirely new dimension of physics. If the electron has an antiparticle, do other particles? The answer turned out to be yes. Essentially, every particle has one. The proton has the antiproton, the neutron has the antineutron, and so on. When a particle meets its antiparticle, they annihilate each other completely, converting all of their mass into pure energy in the form of photons. And the reverse can happen too. Enough concentrated energy can spontaneously produce a particle-antiparticle pair out of nothing but energy. Matter and antimatter, created and destroyed in perfect pairs. Think about what that means for a moment. The boundary between matter and energy is not a wall, it's a revolving door. Energy can become matter, and matter can become energy. And the exchange rate is given by Einstein's famous equation, E equals mc squared. This isn't abstract philosophy. It happens every time a positron meets an electron. It happens in PET scanners in hospitals, where positrons are used in medical imaging. It happens in the hearts of stars. The universe is constantly creating and destroying particles, and the currency it uses is energy. Now, the positron was just the beginning, because cosmic rays, it turned out, were full of surprises. Throughout the 1930s and 1940s, physicists pointed their cloud chambers and photographic emulsions at the sky and kept finding things they didn't expect. And the next shock came almost immediately. In 1936, Carl Anderson, the same Carl Anderson who found the positron, discovered another new particle in cosmic rays. It behaved a lot like an electron. It had the same charge. It interacted with matter in similar ways. But it was about 200 times heavier than an electron. It wasn't a proton, which is almost 2,000 times heavier. It was something in between, something nobody had predicted, something that didn't seem to serve any obvious purpose in the structure of atoms. They called it the mu meson at first, then just the muon. And the physicist I. Rabi, when he heard about it, reportedly responded with one of the most famous lines in the history of physics. Who ordered that? It's a perfect question, because the muon genuinely seemed unnecessary. The universe had electrons for electromagnetic interactions. It had protons and neutrons for building nuclei. What was the muon for? It didn't stick around. It decayed in about 2/millionths of a second, falling apart into an electron and some other particles. It wasn't a building block of anything. It was just there, an extra particle, heavier than an electron but otherwise strangely similar, with no obvious role in the grand scheme of things. And the muon was just the tip of the iceberg, because over the next decade and a half, the trickle of new particle discoveries became a flood. In 1947, a team working with photographic emulsions on a mountaintop in the Pyrenees, Cecil Powell, Cesar Lattes, and Giuseppe Occhialini, discovered the pion, also called the P meson. Now, this one had actually been predicted. Back in 1935, a Japanese physicist named Hideki Yukawa had proposed a theory of the strong nuclear force, the force that holds protons and neutrons together in the nucleus. Remember that puzzle we talked about earlier? The one about what keeps all those positively charged protons from flying apart? Yukawa said there must be a new force, much stronger than electromagnetism, but operating only over very short distances, about the size of a nucleus. And he said, this force must be carried by a particle, a mediator, the same way electromagnetism is carried by photons. He calculated that the carrier particle should have a mass of about 200 electron masses, somewhere between the electron and the proton, and the pion, when it was found, fit the bill almost perfectly. Yukawa won the Nobel Prize in 1949, the first Japanese Nobel laureate. But the pion was not the end. Far from it. Starting in the late 1940s and accelerating through the 1950s, physicists began discovering new particles at an almost alarming rate. There were kaons, strange particles that were produced quickly in high-energy collisions, but decayed strangely slowly, as if they were created by one force and decayed by a different, weaker one. There were lambda particles, sigma particles, xi particles, each with its own mass, its own charge, its own lifetime, its own peculiar behaviors. There were resonances, extremely short-lived particles, that existed for only a trillionth of a second before decaying, so fleeting that they could only be detected as bumps on a graph of collision products. And the discoveries were no longer coming just from cosmic rays. By the 1950s, physicists had built particle accelerators, machines that could accelerate charged particles to enormous energies and slam them into targets or into each other. The basic idea is simple, even if the engineering is staggering. You take a particle, a proton, say, and you use electric fields to push it, making it go faster and faster. You use magnets to steer it in a circle so it keeps coming back for another push. Each time around, it gains a little more energy. The bigger the circle, the more energy you can reach. And when you finally crash that high-energy proton into something, the energy of the collision can create entirely new particles, things that don't normally exist, things that are too heavy and too unstable to be found in ordinary matter, but that spring into existence briefly when enough energy is concentrated in one place. The first circular accelerator was the cyclotron, invented by Ernest Lawrence at the University of California, Berkeley, in 1932. It was just a few inches across, but the machines got bigger, fast. By the 1950s, accelerators like the Cosmotron at Brookhaven National Laboratory on Long Island and the Bevatron at Berkeley were reaching energies sufficient to create protons and antiprotons and a whole zoo of other particles. And the data was pouring in, experiment after experiment revealing new particles with new properties. Physicists started calling it the particle zoo, and the name fit because by the early 1960s, the zoo had grown to contain well over 100 different species of particle. It was a mess, a glorious, chaotic, bewildering mess. There was no organizing principle, no periodic table of particles, no underlying logic that anyone could see. It was as if you'd been told the universe was simple. Electron, proton, neutron, 3 particles, clean and elegant. And then someone opened a door and showed you a room full of confetti. Where did all these particles come from? Were they all truly fundamental? Were they all equally basic, equally irreducible? Or were some of them made of smaller things, the way atoms turned out to be made of electrons, protons, and neutrons? This is the question that would dominate particle physics for the next 2 decades, and the person who did more than anyone else to answer it was a brilliant, brash, supremely confident American physicist named Murray Gell-Mann. And Gell-Mann is worth spending some time with, because he's one of the most fascinating characters in 20th century science, a man of extraordinary intellect and equally extraordinary ego, who spoke multiple languages, was obsessed with etymology and bird-watching and fine wines, and who had a knack for seeing patterns where everyone else saw chaos. Gell-Mann was born in 1929 in Manhattan, the son of Austrian immigrants. He was a prodigy. He entered Yale at 15, got his PhD from MIT at 21, and was a full professor at Caltech by the time he was 27. He was the kind of person who could make other physicists, people who were themselves geniuses, feel slow. And he was not always gracious about it. He could be cutting, dismissive, impatient with people who didn't keep up. But he was also, undeniably, one of the deepest thinkers in the history of physics, and when he turned his attention to the particle zoo in the late 1950s, he found something beautiful hiding in the mess. What Gell-Mann noticed was that the particles in the zoo, despite their apparent chaos, could be organized into families based on their properties, their charge, their spin, a property called strangeness that described how kaons and other strange particles behaved. When he arranged the particles according to these properties, they fell into neat geometric patterns, groups of 8 mostly. He called his organizing scheme the Eightfold Way, a deliberate reference to the Buddhist Noble Eightfold Path, and the patterns worked remarkably well. Not only did they organize the known particles, they also had gaps, empty slots in the patterns where a particle should exist, but hadn't been discovered yet. It was exactly like the periodic table of elements, where Dmitri Mendeleev had left gaps for elements that were later found. And sure enough, when experimentalists went looking for the particles that the Eightfold Way predicted, they found them, with exactly the properties Gell-Mann had specified. The most dramatic example was the omega- particle. In 1962, Gell-Mann used the Eightfold Way to predict the existence of a particle with specific mass, charge, spin, and strangeness. 2 years later, in 1964, a team at Brookhaven National Laboratory found it in a bubble chamber photograph, with properties matching Gell-Mann's prediction almost exactly. It was a stunning confirmation. The patterns were real. There was order in the zoo after all. But patterns demand explanations. Why do the particles fall into these groups? What's the underlying reason? Mendeleev's periodic table was eventually explained by atomic structure, the number of protons and electrons, and how the electrons arrange themselves in shells. Could the Eightfold Way have a similar explanation? Could these patterns mean that the particles in the zoo are not truly fundamental, that they're actually made of something smaller? In 1964, Gell-Mann proposed exactly that. He suggested that all the particles that feel the strong nuclear force, the protons, neutrons, pions, kaons, lambdas, sigmas, all of them, are not fundamental particles at all. They're made of smaller, more basic constituents. He called these constituents quarks. The name comes from a line in James Joyce's Finnegan's Wake, 3 quarks for muster mark, which is a very Gell-Mann touch. Most physicists would have given them a sensible, descriptive name. Gell-Mann pulled his from an intentionally obscure modernist novel. He liked doing things like that. Now, independently, a younger physicist named George Zweig at CERN had come up with essentially the same idea at the same time, calling his hypothetical constituents aces. But it was Gell-Mann's name that stuck, partly because of his stature in the field, and partly because, honestly, quarks is just a better name than aces. Here's the idea. Gell-Mann proposed that there are 3 types of quarks, which he called up, down, and strange. Each has a fractional electric charge, which was genuinely shocking at the time, because nobody had ever observed a particle with a fraction of the electron's charge. The up quark has a charge of plus 2/3. The down quark has a charge of minus 1/3. The strange quark also has minus 1/3, but is heavier than the down quark and carries the property of strangeness. And by combining these quarks in groups of 2 or 3, you could build every particle in the zoo. A proton, that's 2 up quarks and 1 down quark. Add up the charges. 2/3 plus 2/3 minus 1/3 equals plus 1. That's the proton's charge. A neutron, 1 up quark and 2 down quarks. 2/3 minus 1/3 minus 1/3 equals 0. That's the neutron's charge. Neutral, just as it should be. A pion? That's a quark and an antiquark. Remember antimatter. Each quark has its own antiquark with opposite charge. And the strange particles, the kaons and lambdas and sigmas, are the ones that contain at least one strange quark. The strangeness property that had seemed so mysterious was just a label for the presence of this heavier type of quark. It was beautiful. It was economical. The entire zoo of 100+ particles, all reduced to combinations of 3 types of quarks. 3 quarks, 3 antiquarks, and the rules for combining them. That's all you needed to explain the whole menagerie. And the eightfold way patterns? They emerged naturally from the mathematical symmetries of the 3-quark system. The patterns were telling you about the internal structure all along. But here's the thing, and this is important. When Gell-Mann first proposed quarks, he was careful not to claim they were necessarily real physical objects. He presented them as mathematical entities, useful for organizing the patterns, but not necessarily things you could isolate and hold up and say, "Look, here's a quark." And there was a very good reason for that caution. Nobody had ever seen a quark. Nobody had ever detected a particle with 1/3 or 2/3 the charge of an electron. Quarks, if they existed, seemed to be permanently trapped inside the particles they made up, never appearing on their own. That was deeply strange, and for several years, many physicists treated the quark model as a convenient fiction rather than a description of reality. The first strong evidence that quarks were actually real, not just a bookkeeping device, came from experiments at the Stanford Linear Accelerator Center, known as SLAC, in the late 1960s and early 1970s. The idea was simple in concept, though extraordinarily challenging in practice. You take a beam of high-energy electrons and fire them at protons, and you watch what happens. If the proton is a smooth, featureless blob of charge, the electrons should scatter off it gently, deflecting at small angles. But if the proton has small, hard, point-like objects inside it, some of the electrons should bounce off those internal objects at large angles, the same way Rutherford's alpha particles had bounced off nuclei 60 years earlier. And that's exactly what happened. The experiments at SLAC, led by Jerome Friedman, Henry Kendall, and Richard Taylor, showed that high-energy electrons were scattering off protons at large angles far more often than they should if the proton were a smooth blob. The scattering pattern looked like the proton contained tiny, hard, point-like constituents. The physicists called them partons at first, a deliberately neutral term, suggested by Richard Feynman, who didn't want to commit to calling them quarks just yet. But as the data accumulated and the analysis deepened, it became clear that the partons had exactly the properties that quarks were supposed to have. The right charges, the right spins, the right number of them inside a proton. The partons were quarks. Friedman, Kendall, and Taylor won the Nobel Prize in 1990 for this work, which is sometimes called the deep inelastic scattering experiments, a mouthful of a name for one of the most important experiments in the history of physics. So, quarks are real. They're inside protons and neutrons. But what holds them together? What's the glue? This brings us to the strong force, which is one of the 4 fundamental forces of nature, and by far the most powerful, though it operates only over tiny distances. And understanding the strong force requires us to talk about something called color charge, which is one of those physics terms that has absolutely nothing to do with actual colors, but is wonderfully confusing for anyone hearing it for the first time. Here's the problem that color charge was invented to solve. When you start building particles out of quarks, you quickly run into a contradiction. Take the omega- particle, the one Gell-Mann predicted before it was found. It's made of 3 strange quarks, all with the same flavor, all with the same spin, pointing in the same direction. But there's a fundamental principle in quantum mechanics called the Pauli exclusion principle, which says that no 2 identical fermions, and quarks are fermions, can exist in exactly the same quantum state. It's the reason electrons in an atom fill up different energy levels instead of all piling into the lowest one. And it should mean that you can't have three identical quarks all in the same state inside a particle. The omega minus shouldn't be able to exist unless the quarks aren't actually identical, unless there's a hidden property, some additional quantum number that distinguishes them. And that's what physicists proposed. They said that quarks come in three colors: red, green, and blue. This has nothing to do with actual visible colors. It's just a label, a name for a new kind of charge, analogous to electric charge, but with three varieties instead of one. A strange quark can be red, green, or blue, and if the three strange quarks in an omega minus are each a different color, then they're not in the same quantum state, and the Pauli exclusion principle is satisfied. Problem solved. But the color idea goes much deeper than just fixing a bookkeeping issue. It turns out that color charge is the charge of the strong force, the same way electric charge is the charge of the electromagnetic force. The strong force acts between particles that carry color charge, and it's mediated by its own force-carrying particles, called gluons. The word gluon literally means glue particle, which is about as descriptive as particle physics names ever get. And there are 8 types of gluons, each carrying a combination of color and anticolor. The theory of the strong force, worked out in the early 1970s by physicists including David Gross, Frank Wilczek, and David Pulitzer, is called quantum chromodynamics, or QCD. Chromo for color, dynamics for the study of forces. And QCD is, mathematically, one of the most beautiful and also one of the most ferociously difficult theories in all of physics. It has a structure that's similar to quantum electrodynamics, the theory of the electromagnetic force, but with a crucial twist that makes it behave in wildly different ways. In electromagnetism, the force between two charged particles gets weaker as they move farther apart. That's intuitive. A magnet on your fridge pulls on a paperclip more strongly when it's close than when it's far away. And at very short distances, when particles are almost on top of each other, the electromagnetic force gets stronger but remains manageable. QCD works differently, almost backwards in fact. At very short distances, when quarks are very close together inside a proton, the strong force between them is actually relatively weak. The quarks can move around almost freely, like marbles rattling around in a bowl. This property is called asymptotic freedom, and its discovery by Gross, Wilczek, and Pulitzer in 1973 was a major breakthrough that earned them the Nobel Prize in 2004. But, and here's the wild part, as you try to pull two quarks apart, the force between them doesn't get weaker. It gets stronger, much stronger. It's like stretching a rubber band. The farther you stretch it, the harder it pulls back. And if you put enough energy into trying to pull two quarks apart, instead of freeing a quark, the energy you've put in is enough to create a new quark-antiquark pair. The rubber band snaps, and instead of getting a free quark, you get a new particle. This is why nobody has ever seen an isolated quark. It's not that quarks are mathematical fictions. They're completely real. We can see them inside protons. We can measure their properties, but they are permanently confined inside the particles they make up. You cannot pull one out, no matter how much energy you use. This phenomenon is called confinement, and it's one of the most remarkable features of the strong force. It means that quarks are, in a sense, prisoners of their own interactions. They exist, they're there, but they can never be alone. Think about how strange that is. Most things in physics, if you pull hard enough, you can separate. You can break a molecule apart into atoms. You can strip electrons off an atom to make ions. You can split a nucleus into individual protons and neutrons. But you cannot, even in principle, even with infinite energy, extract a single quark from a proton and hold it up on its own. The act of trying to remove it creates new quarks that immediately pair up, ensuring you never end up with a bare quark. It's as if nature has an absolute prohibition against isolated color charge, a rule so strict that the universe will create new matter rather than allow it to be broken. And there's one more crucial thing about the strong force that matters for understanding the Standard Model. Remember how I said that particles made of quarks come in groups of 3 quarks or in pairs of a quark and an antiquark? There's a rule governing this. The rule is that only colorless combinations are allowed to exist as free particles. Just like mixing red, green, and blue light gives you white, a particle made of 1 red quark, 1 green quark, and 1 blue quark is color neutral. It has no net color charge. That's a baryon, like a proton or neutron, or you can combine a quark of some color with an antiquark of the corresponding anticolor, a red quark with an anti-red antiquark, say, and that's also color neutral. That's a meson, like a pion. But you can never have a combination that has leftover color charge. No 2 quark particles, no single quarks, only colorless combinations. The universe is, in a deep sense, colorblind. It only allows particles that have balanced their colors to 0. So that's the strong force. The force that holds quarks together inside protons and neutrons. The force that, through a residual effect leaking out of the nucleons, holds protons and neutrons together inside the nucleus. The reason atomic nuclei exist. The reason matter has structure. The reason you have a body lying in that bed right now. Without the strong force, every nucleus in the universe would fly apart instantly, and there would be nothing but a diffuse soup of quarks and electrons, no atoms, no molecules, no chemistry, no biology, no you. It's the most powerful force in nature, and it operates entirely at distances smaller than the diameter of an atomic nucleus. You never feel it. You never see its effects directly. But everything you are depends on it. Now, let's pause for a moment and take stock of where we are. We've got quarks, which come in 3 flavors so far: up, down, and strange. We've got the electron, the muon, and their antiparticles. We've got the strong force, carried by gluons, binding quarks together. We've got the electromagnetic force, carried by photons, governing how charged particles interact. And we've got the basic architecture. Quarks combine to make protons, neutrons, and the whole zoo of heavier particles, while electrons orbit nuclei to make atoms. But we're missing something important. We haven't talked about the weak force yet, and the weak force is where things get really interesting, because it's the force that allows one type of particle to transform into another. It's the alchemist of the particle world, and understanding it is absolutely central to the Standard Model. The weak force is the strangest of the 4 fundamental forces, and for a long time, it was the least understood. It was discovered, in a sense, before anyone even knew what a force was, in the quantum mechanical sense, because the first clue came from radioactivity. Back in the late 1890s, when Henri Becquerel accidentally discovered that uranium could fog a photographic plate without any external energy source, and when Marie and Pierre Curie threw themselves into studying the phenomenon with a dedication that ultimately cost Marie her health, they were seeing the weak force at work, even though nobody would understand it that way for decades. There are several types of radioactive decay, but the one that's most relevant here is beta decay. In beta decay, a neutron inside an atomic nucleus spontaneously transforms into a proton emitting an electron in the process. The nucleus changes its identity, one element transmuting into another, the dream of ancient alchemists, happening naturally, all around us, all the time. Carbon-14 turns into nitrogen-14 through beta decay. It's the process that makes carbon dating possible. And at the particle level, what's happening is that a down quark inside the neutron is turning into an up quark, turning from one type of quark into a different type. That's not something the strong force does. The strong force holds quarks together, but it doesn't change their flavor. And it's not something electromagnetism does either. This is a different force entirely, and it was eventually called the weak force, because it's much, much weaker than the strong force, and even significantly weaker than electromagnetism. But there was a problem with beta decay, and it was a serious one. When physicists carefully measured the energies of the particles involved, the original nucleus, the new nucleus, the emitted electron, the numbers didn't add up. Energy seemed to be going missing. The emitted electrons came out with a range of different energies, sometimes a lot, sometimes very little, when they should all have had the same energy if only the neutron, proton, and electron were involved. Some of the energy was disappearing, and in physics, energy doesn't just disappear. Conservation of energy is one of the most sacrosanct laws in all of science. If the energy books didn't balance, either conservation of energy was wrong, which would be catastrophic for all of physics, or something else was carrying away the missing energy, something invisible, something that wasn't being detected. Niels Bohr, interestingly, was willing to consider that conservation of energy might not hold at the subatomic level. He seriously entertained the idea that energy conservation might be only a statistical law, not an absolute one. But another physicist took a different approach. Wolfgang Pauli, the Austrian-born physicist famous for the exclusion principle and for his biting wit, proposed in 1930 that the missing energy was being carried away by a new particle, one so ghostly, so weakly interacting, that it passed through the detectors without leaving a trace. He called it the neutron at first, but when Chadwick discovered the actual neutron 2 years later and took the name, the Italian physicist Enrico Fermi rechristened Pauli's ghost particle the neutrino, Italian for little neutral one, the neutrino. This is one of the most remarkable particles in all of physics, and it's worth sitting with for a moment. Neutrinos have no electric charge. They have no color charge. They are almost, but not quite, massless. We'll come back to that "not quite" later, because it matters enormously. They interact with other matter only through the weak force and gravity, both of which are so feeble at the scale of individual particles that a neutrino can pass through essentially anything. Right now, as you lie there, about 65 billion neutrinos from the sun are passing through every square centimeter of your body, every second. They passed through the entire Earth on their way to you, barely noticing it was there. A typical neutrino could pass through a wall of lead a light year thick and have a good chance of coming out the other side. They are the ultimate ghosts of the particle world. Pauli himself was somewhat apologetic about proposing the neutrino. He famously said, "I have done a terrible thing. I have postulated a particle that cannot be detected." But he was wrong about that last part. In 1956, Frederick Reines and Clyde Cowan managed to detect neutrinos directly, using a nuclear reactor as a source and a massive tank of water as a target. It was an extraordinarily difficult experiment, requiring years of careful work to distinguish the rare neutrino interactions from the enormous background noise. But they did it. They confirmed that neutrinos exist, that Pauli's ghost was real. Reynes won the Nobel Prize for this work in 1995. Cowan had died by then and couldn't share it. Now, understanding the weak force took decades. It's a weird force. Unlike electromagnetism, which has infinite range, and unlike the strong force, which operates over the diameter of a nucleus, the weak force operates over a range so short that it's about 1,000 times smaller than a proton. Its effects are confined to distances of roughly 10 to the minus 18 meters, and it was Enrico Fermi who wrote down the first mathematical description of the weak force in 1933, a theory of beta decay that treated the process as a point-like interaction. A neutron goes in, a proton, an electron, and a neutrino come out, all from a single point. Fermi's theory worked well at low energies, but it had problems at higher energies. It gave nonsensical predictions, infinite results. When you pushed it too far, something was missing from the picture. What was missing was the force carrier. Just as the electromagnetic force is carried by photons and the strong force is carried by gluons, the weak force has its own carrier particles. But unlike the photon, which is massless, the carriers of the weak force are extremely heavy. There are 3 of them: the W+ boson, the W- boson, and the Z boson. The W bosons carry electric charge, which is unique among force carriers. The photon and gluons are electrically neutral, and the Z boson is neutral. All 3 are enormously massive, roughly 80 to 90 times the mass of a proton. That mass is the reason the weak force has such a short range. A heavier carrier particle can only travel a shorter distance before it has to be reabsorbed thanks to the energy-time uncertainty principle. The photon, being massless, can travel forever, giving electromagnetism its infinite range. The W and Z bosons are so heavy that they can barely make it across a fraction of a proton's diameter. But here's where the story takes a stunning turn, because in the 1960s, 3 physicists, working partly independently, partly in conversation with each other, showed something nobody expected. The weak force and the electromagnetic force, which seem completely different from each other, are actually 2 aspects of the same underlying force. They are unified. At low energies, they look different, behave differently, have different ranges and different strengths. But at very high energies, the kind of energies that existed in the early universe, fractions of a second after the Big Bang, they merge into a single force, called the electroweak force. The 3 physicists who worked this out were Sheldon Glashow, Abdus Salam, and Steven Weinberg, and they shared the Nobel Prize for it in 1979. Glashow was an American, born in the Bronx, who had been classmates with Weinberg at the Bronx High School of Science, which is an almost absurdly distinguished high school that has produced more Nobel laureates than most countries. Weinberg was also American, a Texan by adoption, known for his beautiful prose. He wrote one of the great popular science books, The First 3 Minutes, about the early universe. And Salam was Pakistani, born in Jhang in what was then British India, the first Pakistani to win a Nobel Prize, a man who spent his career trying to build scientific institutions in the developing world, and who founded the International Center for Theoretical Physics in Trieste, Italy, which has trained thousands of scientists from around the world. What Glashow, Salam, and Weinberg showed was that electromagnetism and the weak force can be described by a single mathematical framework, a unified gauge theory. At high enough energies, the distinction between the photon and the W and Z bosons dissolves. They're all part of the same family. But at lower energies, the energies of our everyday world, a process called symmetry breaking splits them apart, giving the W and Z bosons their enormous masses, while leaving the photon massless. It's as if there's a beautiful symmetry in the laws of physics, a symmetry where all four of these force carriers are treated equally. But that symmetry is hidden, broken, in the world we actually live in. The symmetry is there in the equations, but it's not there in the particles we observe. And that breaking, that hiding, is where the Higgs mechanism comes in. And honestly, the Higgs mechanism might be the most conceptually subtle idea in all of particle physics. It's also, thanks to the popular press, one of the most poorly understood. People sometimes call the Higgs boson the God particle, a nickname that physicists almost universally despise, and which tells you nothing about what it actually does. So let's take our time with this one. The problem the Higgs mechanism solves is this: how do the W and Z bosons get their masses? Why are they so heavy when the photon, which is their cousin, their sibling in the electroweak family, is massless? You can't just put the masses into the equations by hand, because if you try, you break the mathematical consistency of the theory. The gauge symmetry that makes the theory work requires the force carriers to be massless. But the W and Z clearly aren't massless. They're among the heaviest particles we know. Something has to give mass to the W and Z bosons without destroying the symmetry of the theory. The solution was proposed in 1964 by several groups of physicists working independently. Peter Higgs, a quiet British physicist at the University of Edinburgh, published a short paper describing the mechanism. So did François Englert and Robert Brout in Belgium, and so did Gerald Guralnick, Carl Hagen, and Tom Kibble in London. It's one of those cases where an idea was clearly in the air. Several people arrived at it nearly simultaneously, which usually means the time was right. Here's the idea, in broad strokes. Imagine that the entire universe is permeated by a field, a quantum field, like an electromagnetic field but different. This field fills all of space. It has a non-zero value everywhere, even in what we'd think of as empty vacuum. It's part of the fabric of reality. Now, when particles move through this field, some of them interact with it, and that interaction slows them down, makes them behave as if they have mass. The more strongly a particle interacts with the Higgs field, the more mass it acquires. Particles that don't interact with it at all, like the photon, remain massless. Think of it this way. Imagine a room full of people at a party. A nobody walks through the room easily, barely interacting with anyone. That's like a massless particle moving through the Higgs field. But a celebrity walks in, and everyone clusters around them, slowing them down, making it harder for them to get across the room. That resistance, that dragging effect, is analogous to mass. The celebrity interacts strongly with the crowd, so they acquire a lot of mass. It's not a perfect analogy. No analogy for the Higgs field is perfect, because the actual mechanism involves quantum field theory in ways that are difficult to translate into everyday language, but it captures the essential idea. Mass is not an intrinsic property of a particle in the way we normally think of it. It's a consequence of how that particle interacts with a field that fills all of space. The W and Z bosons interact strongly with the Higgs field, so they're heavy. The photon doesn't interact with it, so it's massless. And the quarks and electrons interact with it to varying degrees, giving each of them their characteristic masses. The up quark is light. The top quark is staggeringly heavy, roughly as heavy as a whole gold atom, all packed into a single subatomic particle. The difference comes from how strongly each particle couples to the Higgs field. Now, the Higgs field is a quantum field, and like all quantum fields, it has a particle associated with it, a quantized excitation of the field. That particle is the Higgs boson. Finding the Higgs boson would confirm that the Higgs field exists, which would confirm the mechanism by which particles acquire their masses, which would complete the Standard Model. And so began one of the longest, most expensive, most determined experimental hunts in the history of science. But before we get to the hunt for the Higgs, let's step back and look at the full picture. Because by the mid-1970s, the Standard Model was coming together, and it's worth seeing the whole architecture at once. It's like a building that took decades to construct, and now we can stand back and look at the whole thing, the way it all fits together. So let me walk you through the roster, the full cast of characters. And if you're getting sleepy, that's perfectly fine. Just let the names and the patterns wash over you. There's something almost soothing about the structure of the Standard Model once you see it laid out, because despite all the complexity, it has a deep, quiet symmetry to it. The matter particles, the particles that make up stuff, come in two families. There are the quarks, which feel the strong force, and there are the leptons, which don't. And each family comes in 3 generations, like 3 carbon copies, each heavier than the last, each more unstable, each more exotic. The first generation is the everyday generation. It's the one that makes up you and me and everything we see in normal life. It contains the up quark and the down quark, the 2 flavors that build protons and neutrons. It also contains the electron, which orbits nuclei to make atoms. And it contains the electron neutrino, that ghostly particle we talked about earlier, the one Pauli reluctantly postulated, and that pours through you by the trillions every second. That's it for the first generation. 2 quarks, 2 leptons, 4 particles. And these 4 particles, together with the force carriers and the Higgs boson, are sufficient to build everything you've ever seen. Every mountain, every ocean, every blade of grass, every cell in your body. The entire world of normal experience runs on the first generation. The other 2 generations are, in a sense, heavier, unstable reruns that almost immediately decay back into first-generation particles. They don't stick around long enough to build anything lasting. They're fleeting visitors, not permanent residents. The second generation parallels the first, but heavier. Instead of the up quark, you have the charm quark, which has the same charge as the up quark, but is roughly 500 times heavier. Instead of the down quark, you have the strange quark, Gell-Mann's strange quark, heavier than the down, but with the same charge. Instead of the electron, you have the muon, that heavier cousin of the electron that I. Rabi was so perplexed by. And instead of the electron neutrino, you have the muon neutrino, which is the neutrino that's associated with the muon in weak interactions. And then there's the third generation, heavier still, the top quark, which is extraordinarily massive, the heaviest fundamental particle known. The bottom quark, also called the beauty quark, because physicists sometimes have a poetic streak. The tau lepton, a heavier version of the electron and muon, discovered in 1975 by Martin Pearl at Stanford, and the tau neutrino, the last of the 3 neutrino flavors. So the matter content of the Standard Model is 6 quarks, 6 leptons, arranged in 3 generations of 2 quarks and 2 leptons each, plus all their antiparticles. And then, on top of that, you have the force carriers, the photon for electromagnetism, the W+, W-, and Z bosons for the weak force, and 8 gluons for the strong force, and finally, the Higgs boson, which is in a category by itself. Total it all up and you get 17 fundamental particles, which is the number I mentioned at the very beginning of tonight's conversation. 17 particles. That's the Standard Model's roster. That's everything. Now, the discovery of each of these particles is a story in itself. and many of them took years or decades of experimental effort. Let me tell you about a few of them, because the experimental side of particle physics is, honestly, one of the great underappreciated dramas of modern science. The theorists get most of the fame, but it's the experimentalists who actually find the particles, who build the machines, who sift through the data, who confirm or refute the predictions. And the machines they build are among the most extraordinary technological achievements in human history. The charm quark, the second-generation partner of the up quark, was discovered in November 1974 in one of the most dramatic episodes in the history of particle physics. Two teams, working independently, found it at almost exactly the same time. At Brookhaven National Laboratory on Long Island, a team led by Samuel Ting had been painstakingly studying electron-positron pairs produced in proton collisions. They found a sharp, narrow spike in their data at a specific energy, a resonance, indicating a new particle. Ting called it the J particle. Meanwhile, at SLAC in California, Burton Richter's team was running electrons and positrons head-on into each other in a collider, and they found the same particle from the other direction. Richter called it the psi particle. When the two groups learned about each other's results, the discovery became known as the J-psi particle. Awkwardly hyphenated, both names stuck together because neither team was willing to give up their name. And the J-psi turned out to be a meson made of a charm quark and a charm antiquark, bound together by the strong force. The discovery of charm was the first confirmation that the second generation of quarks was real, and it earned Ting and Richter a shared Nobel Prize in 1976. The discovery is sometimes called the November Revolution because it happened so fast, was so unexpected, and so decisively confirmed the quark model that it changed the entire direction of particle physics almost overnight. Before the J-psi, many physicists were still skeptical of quarks. After it, the debate was essentially over. Quarks were real. The standard model was on solid ground. The bottom quark came next, discovered in 1977 by Leon Lederman's team at Fermilab near Chicago. They found it as a resonance called the upsilon, a bound state of a bottom quark and a bottom antiquark. Then the tau lepton, discovered by Martin Pearl in 1975 at SLAC. Then the tau neutrino, which wasn't directly detected until the year 2000 by the donut experiment at Fermilab, making it one of the last standard model particles to be observed. And then there was the top quark. The top quark is a beast. It's the heaviest fundamental particle known, with a mass of about 173 GeV, which translates to roughly the mass of an entire gold atom concentrated in a single subatomic point. To produce something that heavy, you need an enormous amount of collision energy, and for years, no accelerator was powerful enough. The top quark was finally discovered in 1995, jointly by the CDF and D0 experiments at Fermilab's Tevatron, which was the most powerful particle collider in the world at the time. The discovery was the culmination of a nearly 20-year search and required analyzing millions upon millions of collision events to find the handful that bore the unmistakable signature of top quark production. It was like searching for a single specific grain of sand on a beach, if that grain of sand existed for only a trillionth of a second before disintegrating. The W and Z bosons, the carriers of the weak force, were also major experimental triumphs. Their discovery came in 1983 at CERN, the European Organization for Nuclear Research, which sits astride the French-Swiss border near Geneva. The experiment was led by Carlo Rubbia, an Italian physicist with the energy and determination of a small hurricane, and the detector was designed and built by a team led by Simon van der Meer, a Dutch engineer who had invented a technique called stochastic cooling that made the collider work. What they did was take CERN's existing proton synchrotron and convert it into a proton-antiproton collider, smashing protons and antiprotons head-on to produce enough energy to create the massive W and Z bosons. When the data came in and the signals were clear, the W boson at about 80 GeV and the Z at about 91 GeV, matching the predictions of the electroweak theory beautifully, it was one of those moments where decades of theoretical work and decades of experimental work came together in triumph. Rubia and van der Meer shared the Nobel Prize in 1984, less than a year after the discovery, which is unusually fast for a Nobel. And each of these discoveries, the charm quark, the bottom quark, the top quark, the W and Z bosons, the tau lepton, each one was another brick in the wall of the Standard Model, another confirmation that this theory, this mathematical framework built on gauge symmetries and quantum field theory and the Higgs mechanism, was correctly describing the fundamental structure of the universe. The predictions kept being confirmed. The particles kept showing up with the right masses and the right properties. By the 1990s, the Standard Model had passed every experimental test thrown at it, often with extraordinary precision. And I want to emphasize that precision, because it's really something. The Standard Model isn't just roughly right. It's precise to a degree that borders on absurd. Take the magnetic moment of the electron, for example. Quantum electrodynamics, the piece of the Standard Model that describes electromagnetic interactions, predicts this number to more than 10 decimal places, and the experiments match, to more than 10 decimal places. That's like predicting the distance from New York to Los Angeles and getting it right to within the width of a human hair. No other theory in the history of science has achieved that kind of agreement between prediction and measurement. When people call the Standard Model the most successful theory in physics, this is what they mean. Not that it's popular or elegant, though it is certainly elegant in its way, but that it works to a degree of precision that is almost eerie. There was also a beautiful experiment at CERN in the late 1980s and early 1990s, using a machine called LEP, the Large Electron Positron Collider. LEP was a circular tunnel, 27 kilometers in circumference, running underneath the French-Swiss countryside, in which electrons and positrons were accelerated to high energies and smashed together. One of the things LEP measured was the properties of the Z boson with extraordinary precision. And one of the things those measurements showed was that there are exactly 3 generations of neutrinos. Not 2, not 4, not 5. 3. The way they figured this out is beautiful. When you produce Z bosons and measure how quickly they decay, the decay rate depends on how many different types of lightweight particles the Z can decay into. Each additional neutrino type would speed up the decay by a measurable amount. The data said 3. The Standard Model said 3. Another perfect match. Think about that. We can tell how many kinds of invisible, ghostly, barely interacting neutrinos exist in the universe by carefully measuring how fast a different particle falls apart. That's the kind of indirect, elegant reasoning that particle physics excels at. You can't see the neutrinos. You can't catch them. But you can see their shadow in other measurements. And from that shadow, you can count them. It's like counting the number of invisible guests at a party by noticing how fast the food disappears. The principle is simple, but the execution required one of the most sophisticated particle detectors ever built and some of the most careful measurements in the history of experimental physics. So by the turn of the millennium, the Standard Model was almost complete. Almost every predicted particle had been found. Every predicted interaction had been confirmed. Every precision measurement had come out right. There was just one piece missing, one particle that the theory demanded but nobody had ever seen: the Higgs boson. And the search for the Higgs boson is one of the great sagas of modern science. A quest that took nearly 50 years, cost billions of dollars, involved thousands of physicists from around the world, and required building the largest, most complex machine ever constructed by human beings. That machine is the Large Hadron Collider, the LHC, and just describing it is enough to make your head spin. The LHC sits in the same 27-kilometer tunnel that once housed the LAP Collider, running beneath the countryside near Geneva, crossing the French-Swiss border 4 times on each lap. But where LHC collided electrons and positrons, lightweight particles that produce clean, precise collisions, the LHC collides protons, which are nearly 2,000 times heavier. More mass means more energy, and more energy means the ability to create heavier particles, including, potentially, the Higgs boson, whose mass had not been precisely predicted, but was expected to be somewhere in the range of 100 to 200 times the mass of a proton. The numbers involved in the LHC are almost incomprehensible. 2 beams of protons circulate in opposite directions around the ring, each beam containing about 300 trillion protons arranged in tight bunches. These protons travel at 99.999991% of the speed of light, which means they make 11,000 laps of the 27-kilometer ring every single second. The beams are steered by over 1,000 superconducting magnets, cooled to a temperature of 1.9 Kelvin, colder than outer space, colder than the cosmic microwave background radiation that fills the universe. These magnets generate fields of about 8 Tesla, more than 100,000 times stronger than the Earth's magnetic field. And when the 2 beams cross at designated collision points, about 600 million collisions occur every second. 600 million collisions per second. Each collision produces a spray of particles. The particles fly outward and pass through enormous detectors, instruments the size of apartment buildings, weighing thousands of tons, made of millions of individual sensor elements that record the trajectory, energy, and identity of as many particles as possible. The detectors generate about a petabyte of data per second, which is so much that most of it has to be thrown away in real time, filtered by fast electronics that decide which collisions look interesting and which can be discarded. The ones that survive this filter are stored and analyzed by a worldwide network of computers, involving tens of thousands of scientists at hundreds of institutions in dozens of countries. That's the LHC, a machine that took decades to design and build, that represents the combined efforts of essentially the entire global particle physics community, all focused on one central question among others: does the Higgs boson exist? The LHC started colliding protons in 2010, after a troubled start in 2008, when a faulty electrical connection caused a helium leak that damaged part of the machine and delayed operations by over a year. But once it was running, the data began to accumulate. 2 of the main experiments at the LHC, called ATLAS and CMS, were both designed to search for the Higgs boson, and they approached the search from slightly different angles, with different detector designs, providing a crucial cross-check on each other's results. Neither team knew what the other was finding until the results were made public, which was essential for ensuring that any discovery was real and not the result of some subtle systematic error that might affect one experiment but not the other. The way you search for the Higgs boson is indirect, because the Higgs, if it exists, is fantastically unstable. It would be produced in a proton-proton collision and then decay almost immediately, in about a 10/60th of a second, into other particles. You never see the Higgs itself. You see the particles it decays into, and you try to work backwards. If the Higgs decays into 2 photons, for example, then you look for pairs of high-energy photons in your data and check whether there are more of them at a particular combined energy than you'd expect from all the other processes that can also produce photon pairs. If there's an excess, a bump on the graph at a specific energy, that's your signal. The bump tells you that something with that mass was being produced and decaying into photon pairs, and if the bump is in the right place and the right shape, it's the Higgs. Finding that bump requires separating an incredibly faint signal from an enormous background. For every Higgs boson produced at the LHC, there are roughly 10 billion other collisions that produce debris that looks nothing like a Higgs. You're searching for one particular event in 10 billion. It's like trying to hear someone whispering your name in the middle of a rock concert while wearing earplugs, while the person whispering is also standing a mile away. You need vast amounts of data and exquisite statistical analysis. And on July 4, 2012, the physics world gathered at CERN for an announcement. Both ATLAS and CMS had found the same thing, a new particle with a mass of about 125 GeV, decaying in the ways the Higgs boson was predicted to decay. The statistical significance of the signal was 5 sigma, meaning the probability that the signal was a random fluctuation rather than a real particle was less than 1 in 3.5 million. In physics, 5 sigma is the gold standard for discovery. It's the threshold that separates "interesting hint" from "we found it." Peter Higgs was there, in the audience. He was 83 years old. He had proposed the mechanism in 1964, nearly half a century earlier, and had spent most of that time as a relatively quiet, modest figure in the world of physics. Not one of the flashy public intellectuals, but a careful, understated thinker who had contributed one of the deepest ideas in the theory, and then largely gone back to a normal academic life. When the announcement was made, cameras showed him wiping away tears. François Englert, who had independently proposed the same mechanism with Robert Brout, was also in attendance. Brout had passed away the year before and didn't get to see the discovery. Higgs and Englert shared the Nobel Prize in 2013. The discovery of the Higgs boson was the last missing piece of the Standard Model. With it, every particle the theory predicted had been found. Every force carrier had been detected. Every generation of quarks and leptons had been confirmed. The most ambitious theoretical framework in the history of physics was complete. The building was finished, and it was magnificent. And yet, physicists know that the Standard Model is not the final answer. It can't be, because despite its extraordinary success, its precision, its predictive power, its ability to describe virtually every experiment we've ever performed in particle physics, the Standard Model has glaring holes. Questions it cannot answer, phenomena it cannot explain. And those holes, those unanswered questions, are what keep particle physicists up at night. The reason the LHC is still running, the reason people are designing new experiments and dreaming of new accelerators. The Standard Model is the best map of the subatomic world we've ever drawn, but there are large regions of that map that are still blank. Let me tell you about the blank spots. Because they're fascinating, and they point toward the physics of the future, the physics that someone, someday, will figure out. And if you're still awake at this point, just let these mysteries settle in. They're the kind of things that are worth falling asleep thinking about. The first and most obvious missing piece is gravity. The Standard Model describes 3 of the 4 known fundamental forces: electromagnetism, the weak force, and the strong force. It says nothing about gravity, nothing. The force that holds you in your bed right now, The force that keeps the Earth orbiting the Sun, the force that shapes galaxies and governs the large-scale structure of the entire universe, the Standard Model simply doesn't include it. General relativity, Einstein's theory of gravity, describes gravity beautifully at large scales, but it's a classical theory, not a quantum one. And every attempt to combine general relativity with quantum mechanics to create a quantum theory of gravity has, so far, failed to produce a complete, consistent result. The two great pillars of 20th century physics, quantum mechanics and general relativity, are each extraordinarily successful in their own domains, but they are fundamentally incompatible with each other. They use different mathematics, different assumptions, different languages. Unifying them is widely considered the single biggest open problem in fundamental physics. Now, in practice, this incompatibility doesn't usually cause problems. Gravity is so incredibly weak compared to the other forces that at the scale of individual particles, it's completely negligible. The gravitational attraction between two protons is roughly 10 to the 36th power, that's a 1 followed by 36 zeros, times weaker than the electromagnetic repulsion between them. So for the purposes of particle physics experiments, you can completely ignore gravity, and the Standard Model works perfectly. But there are situations where both quantum mechanics and gravity matter simultaneously. Inside black holes, for example, or at the very beginning of the universe, when all matter was compressed into an unimaginably tiny, dense state. And in those situations, neither theory alone is adequate, and we simply don't have a framework that works. The second big mystery is dark matter. We know, from astronomical observations that have been accumulating since the 1930s, that the matter we can see, stars, planets, gas clouds, everything made of the atoms described by the Standard Model, accounts for only about 5% of the total energy content of the universe. About 27% is something called dark matter, which has mass and exerts gravitational pull, but doesn't interact with light or with any of the Standard Model forces in any way we've been able to detect. We can see its gravitational effects. It holds galaxies together. Without it, galaxies would spin apart. It bends the path of light through gravitational lensing. It left its imprint on the cosmic microwave background, the faint afterglow of the Big Bang. The evidence for dark matter is overwhelming, but we don't know what it is. It's not made of any of the 17 particles in the Standard Model. It's something else, something new. Physicists have proposed many candidates for dark matter particles. There are WIMPs, weakly interacting massive particles, which would be heavy, neutral particles that interact through the weak force and gravity, but nothing else. There are axions, much lighter hypothetical particles originally proposed to solve a separate problem in QCD, called the strong CP problem. There are sterile neutrinos, hypothetical neutrinos that don't interact through any of the Standard Model forces except gravity. Numerous experiments around the world are searching for these candidates, using detectors buried deep underground to shield them from cosmic rays, or using the LHC itself to try to produce dark matter particles in collisions. So far, nothing has been found. The dark matter mystery remains wide open. And then there's dark energy, which is even more mysterious. About 68% of the universe's energy content is in this form, a mysterious something that permeates all of space and is causing the expansion of the universe to accelerate. Discovered in 1998 by two independent teams studying distant supernovae, a discovery that won Saul Perlmutter, Brian Schmidt, and Adam Rees the Nobel Prize in 2011, dark energy is frankly baffling. It behaves like a cosmological constant, a uniform energy density filling all of space, But the value that quantum field theory naively predicts for this energy density is off from the observed value by a factor of about 10 to the 120. That is the worst prediction in the history of physics. It's sometimes called the vacuum catastrophe, and nobody has a satisfying explanation for it. The Standard Model offers no help here. Then there's the matter-antimatter asymmetry. This is one of the deepest puzzles in all of physics. According to everything we know about the Standard Model, the Big Bang should have produced equal amounts of matter and antimatter. They would have then annihilated each other, leaving behind nothing but radiation, an empty universe, no galaxies, no stars, no planets, no you. But obviously that didn't happen. The universe is full of matter and essentially devoid of antimatter. Some process in the early universe must have slightly favored matter over antimatter, producing maybe one extra particle of matter for every billion matter-antimatter pairs that annihilated. A tiny, tiny asymmetry, but enough to account for every atom in the observable universe. The Standard Model does contain a mechanism for this kind of asymmetry, called CP violation, which has been observed experimentally in the decays of kaons and B mesons. But the amount of CP violation in the Standard Model is far, far too small to account for the observed matter-antimatter imbalance. There must be additional sources of asymmetry beyond what the Standard Model contains. Where they come from, nobody knows. And then there's the mystery of neutrino masses. Remember when I said neutrinos are almost but not quite massless? In the original Standard Model, neutrinos were assumed to be exactly massless. But in the late 1990s and early 2000s, experiments showed that neutrinos can change flavor as they travel. An electron neutrino can spontaneously transform into a muon neutrino or a tau neutrino. This phenomenon is called neutrino oscillation, and it was discovered by Super Kamiokande in Japan and the Sudbury Neutrino Observatory in Canada, work that earned Takaaki Kajita and Arthur MacDonald the Nobel Prize in 2015. And here's the key point. Neutrino oscillation can only happen if neutrinos have mass. If they were exactly massless, they couldn't oscillate. So neutrinos have mass, but the Standard Model doesn't explain why or how. The masses are incredibly tiny, at least 1,000,000 times lighter than the electron, which is itself the lightest charged particle. And the mechanism that gives neutrinos their masses appears to be different from the Higgs mechanism that gives masses to the other particles. This is a hint, possibly, of physics beyond the Standard Model. And finally, there's the question of why. Why these particles? Why these forces? Why 3 generations? Why not 2, or 4, or 17? Why do the quarks and leptons have the specific masses they have? The Standard Model doesn't answer these questions. The masses of the particles are free parameters, numbers that have to be measured experimentally and plugged into the theory by hand. The theory doesn't predict them. It doesn't explain why the top quark is roughly 40,000 times heavier than the up quark, or why the electron is so much lighter than the muon. These masses are what they are, and the Standard Model accepts them without explanation. Physicists find this deeply unsatisfying. A truly fundamental theory, they feel, should predict these numbers, should explain why the universe has these particular particles with these particular properties. The Standard Model describes. It doesn't explain, and the gap between description and explanation is where the frontier of particle physics lies. So what comes next? What's beyond the Standard Model? This is where physics stops being a story of confirmed triumphs and becomes a story of brilliant speculation, unanswered questions, and ongoing searches. And honestly, it's one of the most exciting times to be alive if you care about fundamental physics, because we know The standard model isn't the complete picture, and yet we don't know what the complete picture looks like. We're in the gap between one great theory and whatever comes next, and the next theory, when it finally arrives, will likely reshape our understanding of the universe as profoundly as the standard model itself did. There are several ideas on the table, and let me walk through the most prominent ones, not because we know which is right, we don't, but because they give you a sense of the kinds of thinking that physicists are doing at the frontier. The first, and probably most famous, is supersymmetry, often called SUSY for short. Supersymmetry is a proposed extension of the standard model that says every known particle has a heavier partner, a superpartner, with different spin properties. For every fermion, every quark and lepton, there would be a boson partner. For every boson, every photon and gluon and W and Z, there would be a fermion partner. The names are wonderfully quirky. The superpartner of the electron is the selectron. The superpartner of the quark is the squark. The superpartner of the photon is the photino. The superpartner of the gluon is the gluino, and so on. Why would anyone propose such a thing? Partly because supersymmetry solves several problems with the standard model. It provides natural candidates for dark matter. The lightest superpartner, if it's stable, would be exactly the kind of weakly interacting massive particle that dark matter could be made of. It also stabilizes the Higgs boson mass, resolving what's called the hierarchy problem, the puzzle of why the Higgs boson is so much lighter than the energy scale, where gravity becomes important. Without supersymmetry or something like it, quantum corrections should push the Higgs mass up to enormously high values, and only an incredibly precise cancellation, a fine-tuning of about 1 part in 10 to the 30, would keep it at the value we observe. Supersymmetry provides that cancellation naturally, automatically, because the contributions of the superpartners cancel the problematic quantum corrections from the known particles. It's a beautiful idea. Many theoretical physicists have spent their careers working on it. But here's the thing. So far, the LHC has found no evidence of supersymmetric particles. None. The energy range where the simplest versions of supersymmetry predicted that superpartners should appear has been thoroughly explored, and they're not there. This doesn't definitively rule out supersymmetry. The superpartners could be heavier than the LHC can reach, or the version of supersymmetry that nature uses could be more complicated than the simplest models. But it's fair to say that supersymmetry is under significant pressure from the experimental data, and many physicists who were once enthusiastic about it have become more cautious. Then there's the idea of grand unification. We've already seen how the electromagnetic and weak forces were unified into the electroweak force by Glashow, Weinberg, and Salam. Grand unification goes further, proposing that the strong force is also unified with the electroweak force at very high energies. The idea is that at the unimaginably high temperatures that existed in the first fraction of a second after the Big Bang, all three forces were really one force, described by a single, larger gauge symmetry. As the universe cooled, that symmetry broke in stages, first splitting off the strong force, then splitting the electroweak force into electromagnetism, and the weak force, the same way water freezing can break the rotational symmetry of a liquid into the angular patterns of ice crystals. Grand unified theories, or GUTs, were first proposed in the 1970s, and they make some striking predictions. One is proton decay, the idea that protons are not absolutely stable, but will, given enough time, eventually decay into lighter particles. The predicted lifetime of the proton is staggeringly long, far longer than the current age of the universe, but in principle, it should be detectable with a large enough detector and enough patience. Experiments like Super Kamiokande in Japan have been watching vast quantities of ultra-pure water for decades, looking for the telltale flash of light that would signal a proton decaying. So far, no proton decay has been observed, which means the proton's lifetime is at least 10 to the 34 years or longer. Some versions of grand unification predict lifetimes shorter than that and have been ruled out. Others predict longer lifetimes and remain viable. Another striking prediction of grand unification is that it provides a natural explanation for why the electric charges of quarks and leptons have the values they do. In the Standard Model, the charge of the down quark being exactly -1/3 of the electron's charge seems like a coincidence. In a grand unified theory, it's a consequence of the quarks and leptons being different faces of the same underlying object. The charge values are locked together by the symmetry. That's a deeply satisfying feature, and it's one of the reasons many physicists believe that some form of grand unification is probably correct, even if we can't test it directly with current accelerators, because the unification energy is thought to be about 10 to the 15 GeV, which is roughly 1 trillion times higher than what the LHC can reach. And then there's string theory, which is perhaps the most ambitious and most controversial idea in theoretical physics today. String theory proposes that the fundamental objects in the universe are not point-like particles, but tiny, vibrating strings of energy, incomprehensibly small, about 10 to the -35 meters in length. Different vibrational modes of the string correspond to different particles, the way different vibrational modes of a guitar string produce different musical notes. One mode is an electron, another is a quark, another is a photon. The particles of the Standard Model would all be different notes played on the same fundamental string. The appeal of string theory is that it naturally incorporates gravity. When you work out the mathematics of vibrating strings, you find that one of the vibrational modes corresponds to a massless particle with spin 2, and that's exactly the properties that a graviton, the hypothetical carrier of the gravitational force, should have. String theory is, potentially, the quantum theory of gravity that physicists have been seeking for nearly a century. It unifies all four forces and all particles into a single framework. But string theory comes with baggage. It requires extra dimensions of space, 6 or 7 additional dimensions beyond the 3 of space and 1 of time that we experience. These extra dimensions would be curled up so small that we can't detect them, compactified into geometric shapes called Calabi-Yau manifolds at every point in space, and the number of possible shapes is enormous. Some estimates put it at 10 to the 500 possible geometries, each corresponding to a different possible universe with different particles and forces. This is sometimes called the landscape problem, and it means that string theory, at least as currently understood, doesn't uniquely predict the particles and forces of our universe. It says our universe is possible, but so are an incomprehensibly vast number of others. Whether this is a feature or a bug depends on whom you ask. String theory has also, so far, produced no predictions that can be tested with current or foreseeable experiments. The energy scale at which stringy effects would become visible is the Planck scale, about 10 to the 19 GeV, which is far beyond anything we can achieve with accelerators. This has led to a genuine debate within the physics community about whether string theory is really physics at all, in the sense of being a falsifiable scientific theory, or whether it has become a branch of mathematics. Some physicists argue passionately that string theory has produced profound mathematical insights and has changed how we think about quantum gravity, even if it can't be directly tested yet. Others argue, equally passionately, that a theory that can't be tested isn't really a theory, it's a conjecture, and the field needs to refocus on ideas that make contact with experiment. And there are other approaches too, Loop quantum gravity attempts to quantize space-time itself, treating it not as a smooth continuum, but as a network of discrete loops at the Planck scale. It doesn't start from strings, it starts from general relativity, and tries to apply quantum mechanics directly to the geometry of spacetime. Technicolor theories propose that the Higgs mechanism is not fundamental, but is instead an emergent effect of a new strong force operating at higher energies. There are ideas about extra dimensions that aren't curled up, but are large or even infinite, held out of reach by the way forces propagate through higher dimensional space. There are theories with additional Higgs bosons, theories with new forces, theories with new symmetries. None of these has been confirmed. None has been definitively ruled out. The frontier is wide open, and that's what makes it so thrilling. We know the standard model is incomplete. We know there's more to discover. But we don't know what shape the discovery will take, or whether it will come from a more powerful collider, or from an underground dark matter detector, or from a neutrino experiment, or from an astronomical observation, or from a theoretical insight that reframes everything we thought we knew. The history of particle physics has taught us one lesson above all others. The universe is more subtle, more layered, more surprising than our best guesses. Every time we thought we had reached the bottom, atoms are fundamental, then they aren't. Then protons and neutrons are fundamental, then they aren't. There turned out to be another layer, another set of building blocks, another set of rules, and it's entirely possible, maybe even likely, that the quarks and leptons of the standard model are not the final layer either, that they, too, are made of something smaller, something we haven't imagined yet, or maybe not. Maybe we really have reached the bottom this time. Maybe the standard model's particles truly are fundamental, irreducible, the atoms of Democritus in the most literal sense. And the mysteries that remain, dark matter, dark energy, neutrino masses, the absence of quantum gravity, will be resolved by extending the standard model rather than replacing it. Nobody knows. That's the honest truth. After a century of extraordinary progress, we've built the most precise, most powerful, most successful physical theory ever devised. And we still don't know if we're close to the end or standing at the beginning of something even bigger. And here's what I find most beautiful about all of this. As the night gets quieter and you settle deeper into wherever you are, the particles we've been talking about, the up quarks and down quarks and electrons that make up every atom in your body, they were forged in the first moments after the Big Bang. In the first microsecond of the universe's existence, the temperature was so high that quarks and gluons roamed freely in a state called the quark-gluon plasma, a primordial soup of matter at its most fundamental. As the universe expanded and cooled, the strong force pulled the quarks together into protons and neutrons. Minutes later, in the era of Big Bang nucleosynthesis, those protons and neutrons fused into the nuclei of hydrogen, helium, and traces of lithium. Millions of years after that, gravity pulled those atoms together into clouds that collapsed into the first stars. And inside those stars, nuclear fusion built heavier elements: carbon, nitrogen, oxygen, silicon, iron, each one forged in the nuclear furnace of a stellar core through processes governed entirely by the forces described in the Standard Model. When those first-generation stars died, many of them exploding as supernovae, they scattered those heavy elements into space, seeding the interstellar medium with the raw materials for planets, and, eventually, life. The carbon in your muscles was made in a star. The calcium in your bones was made in a star. The iron in your blood, carrying oxygen to your cells right now as you breathe, was forged in the last moments of a massive star's life. in the cataclysmic fury of a supernova explosion, and then drifted through space for millions of years before being swept up into the cloud of gas and dust that became our solar system. And every step of that process, every fusion reaction in a stellar core, every radioactive decay, every electromagnetic interaction between atoms, every bond formed and broken as chemistry built molecules of increasing complexity, every step was governed by the rules of the Standard Model. The quarks inside your protons are held together by gluons. The protons are held in your nuclei by the residual strong force. Your atoms are held together by electromagnetic attraction between nuclei and electrons. Your molecules are built by electrons sharing themselves between atoms in quantum mechanical bonds. The warmth of your body comes from metabolic reactions that ultimately trace back to electromagnetic interactions at the atomic level. Your neurons fire through the movement of ions across membranes, driven by electric fields. You are, from head to toe, a Standard Model phenomenon, a walking, breathing demonstration of what quarks and leptons and gauge bosons can build when given 14 billion years and the right conditions. The particles don't know they're making you. They're just following the rules. But the rules, those 17 particles and their interactions, are sufficient to produce everything, including a mind that can lie in the dark and wonder about the particles it's made of. That recursive quality, matter becoming complex enough to contemplate its own structure, is maybe the most remarkable thing about the whole story. The universe makes particles. The particles make atoms. The atoms make molecules. The molecules make cells. The cells make brains. And the brains make theories about particles. The circle closes. The snake eats its tail. And somewhere in the quiet mathematics of gauge symmetry and quantum field theory, there's room for wonder. We don't have all the answers. The Standard Model has blank spots, and those blank spots might take decades or centuries to fill. There might be particles we haven't dreamed of, forces we haven't felt, symmetries we haven't noticed. Dark matter is out there, streaming through this room right now, invisible and untouchable, a reminder that most of the universe is still a mystery. And gravity, the oldest and most familiar force, the one Newton wrote down 3.5 centuries ago, is still waiting for its quantum theory, still sitting outside the Standard Model like a guest who hasn't been properly introduced. But look at how far we've come. From Democritus guessing that matter might come in smallest pieces, to Dalton's chemistry, to Thomson's electron, to Rutherford's nucleus, to Chadwick's neutron, to Dirac's positron, to the confusion of the particle zoo, to Gell-Mann's quarks, to Weinberg and Salam's electroweak unification, to the discovery of the Higgs boson in a tunnel under Switzerland. It's a story of human minds reaching down into the smallest scales of reality and finding structure, pattern, beauty, and surprise. Every generation of physicists found something the previous one hadn't imagined, and there's no reason to think that process has stopped. So as you drift off, let this settle. You are lying there, made of about 7 octillion atoms, each one a nucleus of up and down quarks wrapped in gluon fields, surrounded by a cloud of electrons. Those atoms have been around for billions of years. They were inside stars. They were drifting in the cold dark of interstellar space. They were part of the cloud that became the sun and the earth. And now, briefly, they're you. They'll move on eventually, join some other arrangement, become part of something else. But right now, they're arranged in just the right way to be a person, lying in the dark, thinking about particles, and that's a pretty extraordinary thing for a collection of quarks and electrons to be doing. The Standard Model won't tell you why there's something rather than nothing. It won't tell you what dark matter is or why gravity doesn't fit. It won't explain consciousness or give you the meaning of life. But it will tell you, with extraordinary precision, what you're made of and how those pieces interact. It's the most detailed, most accurate, most thoroughly tested account of the fundamental nature of matter that human beings have ever produced. And it was built, piece by people who looked at the universe and refused to stop asking what's inside. Sleep well. The quarks will keep doing their thing while you rest. The gluons will keep binding. The electrons will keep orbiting. The weak force will keep quietly transmuting particles deep inside stars, building the elements that will someday be part of something new. And the Higgs field, that invisible presence filling all of space, will keep doing what it's always done, giving the particles their masses, making the universe heavy enough to hold itself together, making everything possible. It doesn't take a day off. It doesn't need to rest. But you do. So close your eyes, let the physics fade to a comfortable hum, and let the particles carry you wherever you need to go next.